Hello and welcome to lecture video 2A, where we will continue our discussion on multiviews. So far in this module, we've discussed classes of projections with a focus on isometric pictorials and multiviews. We've established that isometric pictorials give a nice 3D view of an object for quick visualization, but they are subject to distortion like foreshortening, and they are not the best for conveying part details such as dimensions. For this reason, we are interested in multiview projections. Multiple two-dimensional multiviews can give us a clear and complete visualization of part features in their true size and shape. Although the 2D views make the part shape less obvious, we can dimension these views in a way that is much less cumbersome than with isometrics, which allows us to convey all the information needed for manufacturing and engineering detail drawings. We will talk about dimensioning and detail drawings in the next video, but for now we will continue discussing multiview conventions that are important in the production and interpretation of such drawings. Specifically, we will look at visualizing edges, surfaces, and special features in multiviews, and we will also look at some additional views that are sometimes seen alongside the standard views we talked about in the previous video, notably auxiliary views, section views, and partial and enlarged views. So let's start off with a quick review. Recall the glass box theory that we used to generate third-angle projections. A key consideration in this strategy is the orientation of the object within the glass box. Not all objects will have 6 clear faces to align with the faces of the glass box, but even if this is the case, we want to orient the object such that the major feature surfaces are perpendicular or parallel to the faces of the glass box. This minimizes the number of hidden lines to make the multiview more easily interpretable, as depicted by the example on this slide. Imagine if we were to rotate this object 45 degrees in any direction, the major feature surfaces would no longer be aligned with our glass box, which would make their interpretation more challenging. In the last video, we also talked about proper selection of the most descriptive view as the front view, which also aims to improve interpretability and to minimize the number of hidden lines in views. And the last topic we discussed was determination of the minimum number of views required to completely describe an object. Now let's take a look at interpreting part features in multiviews in further detail. Starting off with the basics, consider the edge of a part, which is the intersection of two plane surfaces like the one shown in red here. If we viewed this edge from the right, it would be perpendicular to the projection plane and it would appear as a point. If we looked at it from the left, or what we would call the front view, the edge would be parallel to the projection plane and it would appear in its true length. The same is said if we viewed this object from the top, and if we looked at it in any other view, such as the current isometric view that we are seeing, the edge is foreshortened, as we discussed previously. So we can generally say that edges appear as points or lines on multiviews. But recall that straight lines can also represent the limiting elements of curved surfaces. So it's important to cross-reference other views to determine whether you're looking at an edge or a limiting element of a curved surface, as we saw with the last example in the previous lecture video. Next, let's consider how surfaces appear depending on their orientation with respect to the plane of projection. No matter what, a surface or any of its edges cannot appear larger than its true size, but it can appear foreshortened in some cases. There are 3 possible classifications of surfaces based on their orientation in a multiview: normal, inclined, and oblique, and we will look at each in further detail. Normal surfaces, to start, are parallel to one of the planes of projections in a multiview and normal to all the rest, hence their name. As shown by the example on the slide, a normal surface appears as its actual size and shape in one view, which happens to be the top view in this case, and as an edge in the rest. All of the surfaces that we can see in this object are normal surfaces. But if we modify the object slightly to make one of the top surfaces slanted, as done here, we wind up with an inclined surface. An inclined surface is perpendicular to one projection plane, where it appears as an edge, and it is inclined in the other 2, where it appears as foreshortened surfaces. If we go one step further and tilt the inclined surface in another direction, we end up with an oblique surface, an example of which we see here. Oblique surfaces are named as such because they are tipped or tilted to all the principal projection planes, and because of this, they appear as surfaces in all 3 standard views. In all views, the oblique surface is foreshortened, which can present a challenge for dimensioning, one that we will learn to overcome momentarily. For now, let's practice identifying these different classifications of surfaces with this object. We can clearly see surface 5 in all 3 views, so it would be classified as an oblique surface. Surface 3 appears as a foreshortened surface in 2 views and as an edge in the 3rd, so it must be an inclined surface. Finally, all the remaining surfaces are seen in their true size in one view and as edges in all the rest, so these are classified as normal surfaces. Normal surfaces are easy to dimension in the view that they are shown in true size and shape, but what about inclined and oblique surfaces and the features on them? Remember that the whole goal of multiviews is to show features to their true size and shape for dimensioning. Our standard multiview with top, front, and right views don't accomplish this for inclined or oblique surfaces, and this is where auxiliary views come in. An auxiliary view is an orthographic view projected onto any plane other than one of the principal planes. More specifically, we need this new plane to be parallel to the inclined or oblique surface for it to be seen to its true size. There are two subcategories of auxiliary views. First, primary auxiliary views, such as the one shown in this multiview drawing, where the auxiliary view is projected or tipped directly from one of the 6 principal views to give the true size of an inclined surface. Secondary auxiliary views, on the other hand, are projected from a primary auxiliary view to give the true size of an oblique surface. For now, we will focus on primary auxiliary views. Here's another look at the generation of a primary auxiliary view. As usual, the object with the inclined surface is placed inside a glass box. However, now we add an additional plane to our glass box that is parallel to the inclined surface. This object is projected onto all planes as seen before, but before we unfold the box, we have to choose which principal plane we want the auxiliary view to hinge off of. Here we've decided to hinge the projection plane off the frontal view, so when the box is unfolded, we end up with this placement of views where straight construction lines can be drawn relating features on the front and auxiliary view. Note the convention is to show only the inclined surface in the auxiliary view, and again in this example, we have hinged the auxiliary view off the front view, but we could have selected the top or right view for this purpose instead. Here we have 3 different multi-view representations of the same object. In the top drawing, the auxiliary view is hinged off of the top view, while in the bottom drawings, the auxiliary view is hinged off of the front and right views respectively. In any case, note how the hinge lines between the standard view and the auxiliary view are represented and labeled. Another challenge that we might encounter with multiviews is interpreting parts containing internal features. These interior features show up as hidden lines in a standard multiview projection, and because hidden lines can be difficult to interpret and visualize, section views are often used to expose internal features of a part. To understand how a section view is generated, imagine taking a cutting plane and cutting through a part as shown with this cutting plane dividing a part in 2. We then take a viewing direction normal to the cutting plane, as indicated by the arrows, and we remove the portion of the part between the viewer, which is ourselves, and the plane, and we project the remaining portion onto our cutting plane to get our section view. In this multi-view representation, we have our standard view with the cutting plane seen on edge as a thick line with 2 dashes to show the location and viewing direction of the section view, and then we have our section view below. In section views, we use cross-hatching or section lining to indicate the cut material, which we can see in this example as well. With section views, lines that would be visible after making the cut are shown as visible lines, while hidden lines normally aren't shown to keep section views more readable. Here are some more examples of simple section views. To the left we have a ball and socket joint of a C-clamp, where the section view clearly shows the internal ball joint of the socket. To the right, we have a hexagonal ratchet socket, with the section view clearly showing the internal features. In both cases, you'll notice that the section view and cutting planes are labeled using index capital letters. To the left we have section AA, and to the right we have section BB. These labels allow readers to clearly associate the section views with the standard multi-views. Also note that all of these examples are of full section views where the cutting plane passes all the way through the object. Other types of section views include half-section views, where the cutting plane only passes halfway through symmetric parts. And there's also offset section views, which are like full section views, but where the cutting plane is stepped or offset to pass through important features that don't lie on the same plane. Even more types of section views exist, but we will focus on full section views for the purposes of this course. Another scenario that we could encounter while generating multi-views of a part is having a part with very large or very small features, such that it's hard to see all of the features at one scale. In this case, we can use detail views to zoom in on small features for better description. Here we just have to draw a circle around the feature that will be included in the detail view on the main view, as seen by the circle labeled B here. And then in the detailed view, we just had to specify the difference in scale under the view title, as shown here. On the other hand, if you have an object with one very long dimension, like this rod, you could use something called a conventional break, as shown here, to shorten the view of the long dimension. This way, the object can be shown to scale, and other features, such as the small details at the end of the rod, are not left out. So we've covered viewing surfaces and edges in multi-views, as well as additional auxiliary, section, and detail views that aid in visualization of non-normal surfaces, hidden features, and small features respectively. Our last topic on multi-views will be visualizing special features in multi-views, starting with intersections and tangencies. In multi-view drawings, no lines are drawn where planar surfaces join contoured surfaces tangentially, as seen here where this plane is tangent to this cylinder. However, if a planar surface intersects a contoured surface, then a line or an edge is drawn to indicate the intersection. This is something to be aware of when you are reading multi-view drawings. Other depictions of features that you should be aware of is the depiction of fillets and rounds. Recall that a fillet is the inside rounding and a round is an outside rounding on a cast, forged, or plastic part. These are both represented in views where you can see the curve shape, and they are represented as a single line or an edge in other views. Finally, another multi-view convention to be aware of deals with revolved features. In this example, we have a part with radially distributed ribs and holes. If we were to take the true multi-view projection of this object, we can see it looks a little confusing and awkward. So rather than doing this, such views are typically simplified by rotating the radial features along the horizontal or vertical center lines to get a symmetric and therefore more easily interpretable view. You can also see arrows on the top view that clearly indicate how these features have been rotated for the purposes of obtaining the front view. To summarize, in this video, we have covered a number of topics to strengthen our understanding of multi-views. This includes visualizing edges and surfaces in multi-views, learning about additional views that can be included in multi-view drawings, namely auxiliary views, section views, and partial and enlarged views, and finally, visualizing special features in multi-views. You might be asking, why is this important? Well, recall that dimension multi-view drawings are used in the creation of engineering drawings needed for part manufacture. In the next video, we will talk about these engineering drawings and some dimensioning guidelines. So see you then.